And welcome to our official start of data structures for today. We are in the last stretch of the class here, the home stretch, talking about graphs. And last time on Monday, we talked about kind of the high-level motivation and intuition for graphs and some of the applications for things like breadth-first search and Dijkstra's algorithm. The key application to keep in mind when you're thinking about Dijkstra's algorithm is to think about Google Maps. That anytime you, that's just, I think of them as like one and the same thing. If I think about Google Maps, I think about Dijkstra's algorithm. If I think about Dijkstra's algorithm, I think about Google Maps. And for me, at least, that's the easiest way to remember exactly what it does and how to use it. Today in class, we're going to talk about a little bit more detail your homework assignment for this for these graph algorithms, which is about the Risk board game. And we will start by looking at some of the code related to the board game, look in detail about how you can go through the debugging process with on this homework assignment, and like just how the code is all structured together. And then after we do that, we'll look a little bit more in detail about how the breadth-first search and Dijkstra's algorithms actually work, doing an example side by side with pseudo code, walking through exactly what it's going to do. As a reminder, homework-wise, so this week, the homework is not the graph homework that's due this week. Instead, your homework for this week is the that PyPy package homework. Again, my hope is that it's a relatively lighter assignment, so that everybody's super busy right now with end of semester, and a lot of you with thesis. So this will give you a chance to hopefully catch up on other things with the lighter homework assignment this week. And this graph homework assignment, which we're talking about now, is not due this Sunday, but is going to be due a week from this Sunday at the beginning of finals week. So you still have some time to work on it. And it's in terms of the difficulty of this assignment, I would say that it is going to be easier than AVL tree and heap assignment, but probably on the same order of magnitude as the BST assignment. Hopefully they're a little bit more fun since you're getting to play a game and conquer the world, which is always a fun thing to do. I'm going to share my screen now. And one last sort of administrative announcement is just a reminder again that you do have either required reading or watching to do in this class. A little less than half of you have done that so far. And just make sure to get that done. The due date, again, for this is going to be the end of finals week. But because we have a lighter homework load this week, it might be a good time to try to get that in. Okay, so here I have our week 14 folder pulled up, and it's not quite week 14, but that's where I've placed our notes for the graphs and the risk game. So that's what we'll be looking at today. Before doing that though, I want to take a look at this risk repository, which I have opened already in this other tab over here. And one of the things that you'll notice is that this repository is actually forked from a different repo. So all the other assignments in this class have been things that I've implemented from scratch, but this one's a bigger project, and I decided to base it off of this repository right here. You don't have to look at any code inside of this repository in order to complete the assignment, but I just want to highlight a couple of interesting things for you. The first one is about the license file in this repository. That when I first encountered this repo a couple of years ago and decided that I wanted to create an assignment based off of it, there was no license file in this repo. This company, Go Data Driven, had written a blog post about risk and doing data analysis related to risk, and that's how I came up to this repo. And it was clear that their intention was to somehow make this code available to the public for other people to build off of. But because there was no license file, I was not allowed to use this code for some other purpose without their permission. And so I wrote them an email just saying, hey, I want to base your code off of, or create some assignments based off of your code here. Would that be okay? And they said, sure. And they decided to add a license file a year ago. They chose the MIT license. So anybody can do whatever they want with it. But again, whenever you encounter somebody else's repo and they don't have a license file, you have to contact them and get written permission in order to legally use it in the US and most other countries in the world. If you don't do that, and then you open yourself up to lots of legal risks. So this repo, one other thing that I'll say about it is this Ipython Notebook, IPYNB right here stands for Ipython Notebook. This is a cool file that you might want to be interested in taking a look at. What this file is, so I have it opened up in this other tab right here. And this is kind of the original purpose of this repo here, is that this company wanted to demonstrate how to use genetic algorithms to solve different problems. And so as their example, they chose the game of Risk, and they're using genetic algorithms to evolve different artificial intelligence players that develop different sorts of strategies to play Risk with. And this Ipython notebook file walks through how you can use their code to learn about genetic algorithms and create your own fully featured artificial intelligences this way. Again, for our assignment, you don't have to look at this. You don't have to do anything related to genetic algorithms. But this is just kind of a cool thing that you might be interested in.
Mike?
Yeah, go ahead.
I had a question about the open source license.
Sure.
Isn't GitHub as kind of an open source community, isn't it kind of implied that if you post to a public repo in GitHub that you're basically saying anybody, or you're basically like freeing up your code for anyone to see?
So you are freeing up your code for anybody to see, but not for anybody to copy and reuse. So in the same way, when like the New York Times publishes an article and they make it available on the internet, anybody is allowed to come read it, but you're not allowed to then take that article and copy and paste it into your own article and base your own newspaper off of what the New York Times has published. And the reason for that is because the license associated with New York Times articles grants New York Times exclusive access to that text. So anybody's allowed to come onto a repo without a license and read it, but you're not allowed to take that code, copy it somewhere else, and use it for some other purpose. You mentioned that like GitHub is specifically for open source, and actually that's not true. The vast majority of code that is hosted on GitHub is not open source. It is proprietary code that's locked up private repositories behind passwords, and that's how GitHub actually makes all of their money. That people pay, individual users pay something like $10 a month to host their private repositories and get the GitHub actions associated with those repos. And then companies can pay tens to hundreds of thousands a month, depending on how much software that they have posted on GitHub. So it is true that it's useful for open source, but it is not a primarily open source endeavor.
Makes sense.
Great question. Any other questions so far? Okay, then let's come over here to this week 14, where we have all of the instructions related to our risk game. And again, the main learning objectives for this assignment: implementing graph traversal algorithms, so specifically the breadth first search and the Dijkstra's algorithm. One of the things that's sort of unique about these algorithms compared to all the other algorithms that we've talked about in class is that, like sorting algorithms, it's great that we've talked about them, but you should never implement a sorting algorithm. If you're in Python, you use timsort, you use the built-in sorting function, and it's guaranteed to be faster than whatever you're going to write. It's just really, really good optimized code. Similarly, if you need an AVL tree, you don't write it yourself. You use one that somebody else has written, and that's really, really highly optimized. But we'll see with graph traversal algorithms, they are very tightly coupled into the application domain. And so it's impossible to just take an off-the-shelf library for, say, Dijkstra's algorithm and apply it to this code here. Yeah, there's just too much coupling to make that feasible. And so if you need a graph traversal algorithm, it's something that you really will have to implement yourself. Yeah, so we'll see applications to real-world AI problems, and this, again, is using someone else's complex code. So there's going to be a lot of starter code in here, a lot more than the previous assignments that we've had. There's going to be multiple Python files that you're working with. You'll have to read through some documentation to understand what's going on and how to use other people's functions correctly inside of this code. Let's see, we've talked a little bit already about how the game board is represented and structured as a graph. As a reminder, each one of these territories is a node in the graph, and we have an edge between two nodes if it's possible, if those territories are connected somehow. So if they're adjacent to each other, there's an edge, or if there's sort of a bridge crossing the ocean, say between Brazil and North Africa, or Kamchatka and Alaska, and other similar locations, then there's also an edge between them. There's a pretty standard representation for board games. So Monopoly, Settlers of Catan, whatever your favorite board games are, if you were to implement them or create some sort of AI for solving them, the first thing to do is always to represent them as a graph in this way. And now the actual functions that you're going to have to implement are divided into two categories. The first is path verification functions, and then breadth first search functions and Dijkstra's algorithm functions. So in order to talk about these, I'm going to switch now over to the code screen, and we'll take a look. So currently, I am in the Lambda server on both of these terminals, the top one and the bottom one down here. In order to do debugging effectively on this problem, though, you're going to have to SSH into the Lambda server slightly differently than you normally would. So on this bottom terminal down here, I'm going to exit out of the Lambda server. So I'm back on my laptop right now. And now I've just pressed the up arrow to get back to my SSH command right here. And this is the normal SSH command that we've sort of always been doing in this class to connect to the Lambda server. But then I have this -XY flag at the end over here. And what this -XY flag means is that the Lambda server is going to be allowed to open up Windows on my own local computer. And in the context of this assignment, what that means is that it'll be able to display boards and moves of the different pieces on the local computer. So when you connect, you'll want to add this -XY flag on your SSH command. This is for people who are using either Macs or Linux. If you're in PuTTY, then, so a Windows user, then they'll have to find the appropriate checkbox that's equivalent to the XY flag. And it'll be labeled in there somewhere, but it'll be slightly different for each version of PuTTY. So I'll go ahead and relog in, retype in my password. There we go. And now I'll be able to open up Windows on this bottom screen. I'll go back into my risk folder, so cd proj/risk like this, and now we're ready to start. Okay, first of all, are there any questions about this? XY flag. Okay. So here at the top, do ls. There's so a risk folder contains all of the most interesting files to us, the board.py and definitions.py. And then there's this tests folder over here that contains the tests cases. I'm going to start with the test cases. And what I'm going to do is do this, open up the, there's just one Python file here, test_search.py. And at the very beginning of this file, it defines a bunch of boards that are used in the different test cases. And I'm going to go ahead and copy all of these. So in order to get into the visual mode inside of Vim, when I'm at the top, I press Shift-V to go into visual mode. And now I can select all of these boards right here up to board 5. I'll press Y to yank them into Vim's clipboard. And I'm going to now create a new file called examples.py. So tab E examples.py and press P right here to paste all of that content and save that. And the reason I'm doing this is this will give us a file that we can just play around with and modify in order to explore a little bit how the different functions in this repo work. And we'll be applying them to these boards here. And so now down here that I have this examples.py file, I'll just go ahead and run it, examples.py, and you'll see that nothing actually happens. It creates these boards, but it doesn't do anything with them. And so what I want to do, the first thing that I want to do is I want to plot one of these boards and so that we can visualize it and see what's going on. The way to do that is whatever board we want to visualize, it's that board dot plot underscore board like this. And this function call, this method call, will actually generate a board for us to look at. So do that. It's actually a surprisingly slow process to generate this board, but there we go. It takes a second, and here is the resulting board from this code right here. The colors of each of these circles represent the player who is sort of the owner of that territory, and the number inside of the circle is the number of armies that are contained in a territory. So one of the rules of Risk is that every territory must be owned by exactly one country, exactly one player, and every territory must have one or more number of units inside of it. So you'll always have at least one inside all of these circles. In this case, this code has specified that all of these territories belong to player ID equals 1. And so that's the blue player, and so everything is blue. Let's see a different example now. I'm going to delete this line on line 7. So I'll press DD in Vim to delete the line. Now I want to move my cursor down to line 15 right here, but I'm lazy and I don't want to press the down arrow a bunch of times. So I'll type 15GG to move my cursor down here. And when I did the DD command, anytime you delete something inside of Vim, it automatically puts it inside the keyboard, inside the clipboard for you. So you can paste it again really easily. And so I'll press the P command right now to paste that right here. And so really easily, with just like 5 keystrokes, I was able to move this, this full line down to a more appropriate spot. And now it's not board 0 that I want to plot, but board 1. So I need to change this 0 to a 1. So I'm going to move my cursor over to the 0, F0, and now replace that 0 with a 1, R1, never even getting into insert mode in order to do that. And now that we've done that, I want to save this, :W, come down over here, Control-C to end this program, and now we'll rerun it, visualizing this new board. And again, it'll take a couple of seconds to do this. And here you can see now there's still the vast majority of these territories are blue, but now we have one little red territory down here. And there's also a lot of these territories with 500s inside of them. Yeah, so it's a similar board, but different enough that we'll be able to run different test cases on this board compared to the previous one. This illustrates two important functions, two important methods inside of the board class. This setOwner method. Here we're changing the owner of this territory down here, Argentina, to be player 0. And so that's why it's appearing red down here. And then it illustrates this setArmies command, where it's changing the number of armies in each of these positions over here to be 500 instead of whatever it used to be. One of the things that's a little bit maybe counterintuitive at first with this code is that all of these territories are represented by numbers instead of by names. So this territory down here is conventionally called Argentina in the board game because Argentina is the biggest country in this region of Latin America. And Argentina happens to be represented with the number 3 in the board. And so that's why doing setOwner3 changes this territory right here. And then these other territories are represented by the numbers 4, 34, 39, and 35. In order to see exactly how the names of territories map onto the numbers systems, the file that contains that is the definitions.py file. So I'm going to open that up next. And again, in Vim, to open up a new tab, tab E, then the name of the file that I want to open up. The name of the file, it's inside of the risk folder. And I'll press tab again, just to get a list of all the files inside of the risk folder. And it's definitions.py that I want to open up. So I'll press D, press tab to autocomplete that, and then press enter. And here at the very top of this file, definitions.py, you can see this territory names dictionary. And this is the key piece of code that maps all of these numbers to the names of all of these territories, which are a little bit easier to remember and work with. The keys for these territory names are the numbers, so like the 3 representing Argentina, and then the values are the actual names of the territories in the board game. Yeah, so if you're familiar with the Risk game, then you might be familiar with most of these territories, and if you need to say, you know, that this one here is called Middle East, you can find Middle East going down alphabetically to the appropriate spot, Middle East, number 21. And so if you wanted to change the numbers of units on here, you would now know which what numerical value to use to change that. This is really going to be a sort of fundamental thing to understand about how this code is structured. So now is a good time to ask any questions about this mapping, if you have any.
Mike?
Yeah.
I had a question about Vim.
Sure.
Earlier when you were looking at the 0, you did F0, which I think is super handy. And if I'd known that sooner, that would have been super cool. What if there were more than 1 zeros in the line?
Great question. So here, let's, in order to go to the beginning of the line right now, I'll just press 0 to move my cursor to the beginning of the line. And here we have 2 different A's inside of this line. And let's say I wanted to move my cursor to this second A or this first A. Anytime you press the F key and then the name of another letter, it will move you to the next occurrence in the line of that particular letter. So let's move this cursor here to this A, FA, oops, keeping focus on this window, FA moves me there. And now I could type FA again to move me to the next line. But I am a lazy person and I don't want to type FA again. So I'm going to move my cursor back to the beginning and I'll type FA to move me once. And then you can press the semicolon key to repeat your previous find action. If you want to go backwards to the previous A, you can press the comma key to go back to whatever that letter is that you're searching for with the F key, but doing it backwards. Yeah, when doing movements of the cursor, keeping on the same line, this F key is sort of along with the comma and the semicolon, this is the main way that I move around staying on a single line. All of these sort of shortcuts, so like this F key, for example, it is introduced inside of the vim tutor command. But when you first are going through that vim tutor command, it's just like so much information, impossible to take in. And so I recommend, or at least personally, what I found was helpful in order to really get familiar with Vim. I had to redo that Vim tutor command multiple times, sort of when I was first learning, and then a couple months later did it again, and then a year or two later did it again. Every time I do it, there's new things in there that I learn. So if you're feeling on, if I've convinced you to get on the Vim train, you like Vim, want to get a little bit better about it, going back and revisiting the Vim tutor command would be a good way to fill in some of these gaps of things that you might have missed the first time.
Solid. Thanks.
Yep. Great question. Any other questions so far? Okay. So let's keep going through this definitions.py file again. And so in order to switch my tab over to the other side, I'll press GT to move it over. And now, yeah, it's one of the other nice movement commands in Vim is the, what's this key called? The curly braces key. So it's the these keys right here. On the US keyboard, it's above the square bracket key, pressing Shift. And what this command, the left curly brace, the opening curly brace, moves you to the first line of a paragraph. And a paragraph in Vim terminology is anything that is separated by a single blank line. And so it effectively moves you to the next blank line and to the previous blank line. And you may have noticed that in PyLint or in Flake 8, our linter, one of the things that it's very picky about is that you have the appropriate amount of spaces between each of your Python definitions, and you don't have extraneous spaces where they shouldn't be. And the reason for this is so that you can use these paragraph movement commands to go really quickly back and forth between all the different definitions inside of your file. So right now I'm just pressing the curly braces multiple times to move back and forth between all the different definitions inside of this definitions.py file. And so we've talked about territory names right now. This next one is territory neighbors. And this is what actually defines the graph structure of our board here. So again, territory neighbors is a dictionary. The values, or sorry, the keys of the dictionary are the same keys that we had up here for the different territories. Up above, the number associates us with a territory name, but down below, the number associates us with a list of other territories that are neighbors of this particular territory. So territory 1 has as neighbors 26, 2, and 19. So real quick, I don't know off the top of my head what territory 1 is, so let's go find out. I'm going to press the opening curly brace key to jump us back up here. Number 1 is Alaska. And as a neighbor, 1 had 2 as a neighbor, Alberta. And so Alaska is just connected to Alberta right over here, right next to each other. And so that's the meaning of this territory keys. It turns out that in graph data structures, one of the things that's so interesting about graph data structures is that there are many, many ways to represent graphs. Many ways, oh, that's the wrong comment. Many ways to represent graphs. And this particular representation is called an adjacency list representation. This is, let's see, so the textbook talks about adjacency list representations quite a bit, and they compare and contrast them with something called an adjacency matrix representation. In practice, in the computer science world, people who are sort of really practitioners, coders, programmers, engineers, people who just really want to get stuff done, we almost always use the adjacency list representation when we're actually coding things because it has sort of the most intuitive runtime and memory characteristics. The adjacency matrix representation, though, has some mathematical advantages. And this is something that we'll actually talk about in the data mining class if you choose to go on and take that. But in this class, we're not going to talk about the adjacency matrix representation. This is really for, I guess one of the nice things about it is it's easier to prove things about your algorithms, like proving correctness, proving that it's going to do really exotic things, because the proofs end up reducing down to proofs about linear algebra and matrices. But this one here is typically the easier to work with representation. The idea of, or where we get this name, adjacency list representation, is that for every territory, we just have a list of all of the other territories or all of the other nodes that are neighbors of that territory. So it's a fairly intuitive way to represent things. For the Risk board game, one of the properties of Risk is that the graph is going to be an undirected graph. That because Alaska is a neighbor of Alberta, we're also going to have that Alberta is a neighbor of Alaska. So we have this property that for the key of 1, if 2 is in the list, if we go to 2, we will see that 1 is also in the list. So that means 1 is connected to 2, 2 is connected to 1. 3 is connected to 4, and 4 is also connected to 3, and so on. So you'll never have a situation where we have a directed graph in the Risk board game.
Hey, Mike.
Yes.
Is there a reason why the lists aren't in ascending order?
Oh, that's a great question. Questions about the order of elements in this list here. And the answer is that I believe how they chose these, if I'm remembering correctly, is they went like clockwise order in terms of how things are actually located on the, like physically spaced out on the board. But nowhere in their code do they actually make any they don't take advantage of that property anywhere. That you should think of this as just an unordered set. Something's either in it or not in it, and the location does not matter. So yeah, you could reorder them all to be in ascending or descending order, and everything will still work correctly. It's a great question. Another thing that you could do is change all of these to set types. Whoops. Set types instead of list types, and that won't change anything either. If we had a really enormous graph, then the set would be the more efficient thing to do, because membership checking in a set, it takes time O of 1 on average, whereas in a list it takes time O of n on average. But since these are so small, the asymptotics don't really matter. It's the constant factors that'll matter the most, and I'm actually not even sure which would be faster here, a set or a list. But since their code is with lists, that's what we use. Very common in Python to just make everything a list if it's possible, especially if it's small. Great questions. Any other questions so far? Okay. The rest of the definitions inside of this definitions file are relatively unimportant. So this territory locations, just as the XY coordinates here in this image of where each of these dots should be located for the corresponding territory. Continent names and continent bonuses, these are sort of very domain specific things for the Risk board game. And the continent territories, which territories actually map to which continents. For if you were implementing a full AI that was really trying to win the board game, you would have to be aware about all of these things. But for our purposes, we're just going to be implementing one small pathfinding component of an AI, and so we won't need any of these other definitions. Let's see. So the next thing that we'll take a look at is inside of the risk folder, there is this board.py file. And let's take a look at this. One of the first things I always do when I'm checking out a new file is just check out how long is this file, how big of it, how much like mental energy do I think I might have to expend trying to understand this file. So in Vim, I'll press Shift-G to take me to the end of the page, and it's 630 lines long. So there's quite a bit of stuff in this file. My solutions to all of the previous assignments that we've had are all significantly shorter than this. So this file is more complicated than, in some sense, it's more complicated than anything we've seen so far. One of the nice things about this file, though, is that all of these functions have a lot of really good documentation inside of them about what they do, what arguments they take, and what they return. And so most of these 633 lines are actually just documentation telling you how to use the different code in here. Press GG again to take us back to the top, and what I want to look at now is what are the classes inside of this file. So that's another next thing to look at in a file. First, just how big is it? Get the big overall sense. Next is look at what are the classes and what is the class structure. So there's this board class, which is the sort of obvious class in this file. I'm going to go ahead and search for the keyword class to see if there are any other more classes in this file. So slash and then the word class. And you can see that there's a few class methods, but the board is the only thing that has a class. So that's sort of the main thing that I need to try to understand is this board class. One thing that we haven't fully talked about yet, or really talked about at all, is this named tuple. And a named tuple is sort of a shortcut way for creating a kind of miniature class. Named tuple is a shortcut for creating a miniature class. These classes will have no methods. If your class needs to have a method, you don't want to use a named tuple. Instead, you'll want to use this actual class object. And they will only have attributes. So again, the attributes are the variables associated with the class. The first parameter to name tuple is going to be the name of the class. So this is creating a class called territory. Vast majority of times, you want this and this to be the same as each other. But you can see here for attack and move, they're actually different from each other. For our purposes, we're not going to need this class at all, though. We'll just need this territory named tuple. And the elements inside of this named tuple are territory ID, player ID, and armies. So each one of these territories inside of the board is going to be represented with these three values right here. And that's going to fully describe everything that we need to know about the territory. So which actual territory is it? Going back over to the definitions here under territory names, the territory ID corresponds to the keys right here. And then the player ID, it corresponds to the colors down here. So is it red or blue, or I think it supports up to 6 different players. And then the armies is the actual number of inside of this dot, how many units are stationed there. I'm going to take us back to our examples file right here. And here you can see on this board 0 right here, we're creating an instance of the board class. And what we're doing when we do that is we pass in this list of territories. So these territories right here correspond to those named tuples. This board class corresponds to the board class. And then inside of this territory, the reason it's called a named tuple instead of something related to classes is because when you construct it, you construct it this way where it kind of looks like a tuple, only each one of the elements you actually specify the name right here in front of the equal sign. So territory ID equals whatever it is, player ID equals whatever it is, armies equals whatever it is. In the Risk board game, there are 42 different territories. And so the here, this list generator is just going to, or this I value right here will go everywhere from 0 to 41. So that'll be all the territory IDs. We'll set them all to player 1, the blue player. And then this is sort of like a, not really random, but a shuffle different values for the armies. And so that's why we get 1s and 2s and 3s and different values over here. Here, it's very important, this idea of the deep copy right here. And the reason for that is we want, or what I wanted, my intention with this board 1 is that it would have all the same values as this board 0 does at the beginning. But then we wanted to change some of these values of board 1 to be these other values reflected down here. But when I change these things down here, I do not want them to also change board 0. I want board 0 to be fixed and not changing at all. And so that's why I have to create a deep copy of board 0 so that all of these territories will actually also be copied. And when I modify those territories with this set owner and set armies methods, it's not going to modify board 0, but only modify board 1. Are there any questions so far about the setup of this code and how it's structured?
Could you quickly go back to the named tuple line?
Sure. Do you have a question about the line itself, or?
No, I was just writing down like how to go about formatting the line if you wanted to use the name tuple to make a miniature class.
Okay. Let's say I should have mentioned this before, but I didn't. The name tuple is not something that is a keyword in Python. So class is a keyword in Python. Name tuple is a part of this collections library. Collections is built into Python, so you don't have to pip install anything to get access to it. But you do have to import it in order to use this named tuple. And we've seen collections before. In the MapReduce assignment, we used the default dict and the counter class also contained inside of collections. And actually dec is also contained inside of collections. So there's quite a few useful things inside of here. And in this class, we haven't covered all of them, but I would say a proficient Python programmer would know all of the things inside of collections. Great question. Any other questions so far? Okay, then let's look through some of these functions to see what all is inside of this board class. So there's a lot of functions here that you won't have to touch or even think about. So like this create function. And one of the challenges of this assignment is going to be to figure out which of these functions are going to be useful to you and not useful to you. So in a lot of your code, you will have to be thinking about which territories are neighbors of which other territories. And so these neighbors methods are a good source of functions to reference and to use in your code, but you won't have to modify anything inside of this neighbor methods section. But my solution, at least, I heavily call the functions in that section. This path methods is the first section that you're going to have to actually implement. And if you, the first thing is just checking to see, is a path valid? So again, anytime we're doing anything with the data structures, we always, very first thing you do, somehow have a function to check to see, is something valid or not valid? And so in our code, a path is going to be a list of territories, so just a list of numbers, satisfying these two conditions which we talked about last time. I think in particular, in our definition last time, we did this number 1 condition saying that the endpoints must match. But we didn't actually talk about this number 2 condition, no territories repeated multiple times. This is depending on your sort of graph theory definitions that you're using. Sometimes this would be part of the definition of a path, sometimes it would not be. But for our particular application, we would never want to have a path that has a cycle inside of it. And so that's why we've added this condition right here to ensure there are no cycles. Important edge cases are that a path can have only 0 or 1 elements, 0 or 1 edges inside of it, and you'll have to be able to handle those cases. So this is the first function that you'll have to implement. Similarly, for isValidAttackPath, you'll have to implement this as well. And now let's talk about the difference between a valid path and a valid attack path. So an attack path is something that is not like a graph theoretic concept at all. This is a very specific risk concept. And what I mean by an attack path is that it's a path that your armies can follow while they're doing an attack. And if you are not familiar with the Risk board game, then again, there is a link to an online game that I recommend that you try playing just to get yourself familiar with the rules a little bit more, make things a little bit more intuitive. But in Risk, when you have a set of armies, say this blue army right here, you're only allowed to move into a location where your enemies are located. So this blue 500 cannot do an attack on Venezuela or cannot do an attack on Peru, but it can do an attack on Argentina. And so it would be a valid path to go from Brazil to Venezuela, but it would not be a valid attack path to go from Brazil to Venezuela. And so your isValidAttack path is going to look very similar to your isValidPath function, but you'll have this additional check to make sure that you never move through your own same country twice. Sorry, that you never move through the same color. This next path function, the cost of an attack path, this is going to be particularly important for the Dijkstra's algorithm problem. That the cost of an attack path is going to be the total number of armies in all of the paths that you move through. So let's say I am in Argentina down here, and I want to move right over here to North Africa. Well, there's a lot of different paths that I could take to go from Argentina to North Africa. The shortest one from a number of territories perspective would be to go from Argentina to Brazil to North Africa. But here in Brazil, because we have this huge, massive army in our way, it'd be a very risky move. We don't know if we'd be able to win that battle or not. So instead, it would be a more strategic move to go from Argentina to Peru to Venezuela, coming up through here, through North America, coming around to Kamchatka, down through Asia, and into Africa this way. And the cost of the attack path will add up all of these armies and actually return that number to you. Then this shortest path function is the first one that's that you have to implement that's going to be really challenging and interesting. All the ones above should be relatively straightforward once you get a handle on the functions, the helper functions inside this class that you need to call in order to use them. But this shortest path one is the first one that's going to really involve your algorithmic knowledge. Before, well, let's see. Yeah, so what this shortest path function is doing is it's implementing the breadth first search. So it's, if we wanted to say what is the shortest path from Argentina to North Africa, this is ignoring all of the costs of the armies in the way, ignoring both the colors and the numbers. So it would just be Argentina, Brazil, North Africa. Similarly, if we're going from North Africa to Argentina, well, there is actually no attack path from North Africa to Argentina because it's surrounded by blue dots over here, so we can't move in any direction. but the shortest path ignores all of that and just goes North Africa, Brazil, Argentina. The pseudocode for the shortest path is given to you in quite a bit of detail over in our notes over here. And the, so here there's going to be actual two sets of pseudocode that, that we'll look at. This pseudocode is taken directly from our word ladder homework, only I've replaced the words, anytime the word word appeared in the pseudocode, I just replaced that with territory. And anytime the word dictionary appeared in the pseudocode, I replaced that with the word board. This syntax of s/ and then /g at the end is how you do find and replace inside of Vim. And you'll see people all over the internet documentation for various libraries using this notation to just indicate that do this find and replace, and in order to accomplish some particular task. So this code right here is something that you've basically seen before and should be able to implement, not too bad. There's another set of pseudocode though that I want to compare with us side by side. And so let's bring them up side by side and take a look. Here we go. So on the left, I have this same pseudocode for breadth first search. And then on the right, I have a new pseudocode for breadth first search. And this pseudocode for breadth first search is the one that you're going to want to actually implement for this shortest path homework assignment. And there's a couple of reasons for that. The biggest reason is that going from this pseudocode here of breadth first search to the Dijkstra's algorithm pseudocode is going to be really, really straightforward. We'll see that all you have to do is basically just change this queue up here into a heap, and you'll transform magically from breadth first search into Dijkstra's algorithm. So that's the main motivation for rewriting this like this. The other motivation is that this is actually going to be just slightly faster. And yeah. So I'm going to walk through now what are the key, there's 3 key differences between this pseudocode over here and the original pseudocode over here. And the first key difference is you'll notice that there's a dictionary up here and on the right-hand pseudocode that is going to actually store our paths. So here I'm creating a dictionary whose keys are territories and values are paths. Anytime you're creating a dictionary, you always want to be very clear about what are the keys and what are the paths, or what are the keys and the values. So the keys are territories and the values are paths. And in particular, the what these territories are going to look like are going to be those numbers 0 through 41 representing those territory IDs. You do not want to try to use the text values because that'll just make things a little bit more complicated for you. Yeah, again, so it's stored in a dictionary on the right-hand side. On the left-hand side, we had a queue. In that queue, we were storing the paths, and those paths were represented as stacks. On the right-hand side, we still have a queue, but now what we're storing in that queue is not the entire path, but just the end point of the path. Just the end point of the path. In order to get the equivalent value of what was stored in the stack over here, then you would look up in the dictionary at that particular location, and that would get you the full thing that was stored in the queue over here. The second difference between these two pseudocodes is on the right over here. We have a set of visited territories that we are collecting, and every time we visit a territory, we will add a territory into the set. So down here, source is is wherever we're starting at, and so we begin by adding source into the set. And then at the very end of our while loop down here, see it says add current territory to the visited set. So after we visit this territory, basically every iteration through this while loop will visit one territory. And after we visit it, we add it to the visited set. It's a little bit different than
Can I
what we
ask a
did on the
quick
left.
question?
Yes, go ahead.
So when you say you add the endpoint to the queue, isn't source the starting point, or?
So yeah, exactly. Source is the starting point where we're starting at, and there is a particular, this source represents a path starting at source and ending at source. So it's the endpoint of that path, not the endpoint of the entire thing that we're looking for, but just the endpoint of one particular path that's getting stored in the queue each time. And in particular, it'll be whatever node that we're visiting inside of this visited territories list. That's going to be the same node that's going to be added into the queue. Yeah, good question. So yeah, we have our visited set on the right-hand side. And the way on the left-hand side that we're keeping track of which words we visited, or which, in this case, territories we visited, is that we were deleting the territory from the board, or in the previous assignment, deleting the word from the dictionary. That worked for the previous assignment because we were only going to use that dictionary once and we didn't need to reuse it again. But for this board, we're gonna, after you say plan out one move, you're gonna need to be able to plan out a new move later on. And so you don't wanna be deleting things from the board, deleting territories from the board, because then you won't have access to them later on. So in general, it's a little bit better practice to, rather than deleting, just to have a visited set and keep track of things that way. The last change is this inner for loop. So here you can see that this for loop on the right-hand side says for each territory in the neighbors of the current territory. And current territory is whatever you have most recently extracted from the queue. Here, our for loop goes over each of those neighbors explicitly. In the left-hand side, we so dequeued a stack from the queue. This stack and this current territory are sort of, they're not exactly the same. They're not exactly the same thing, but they're like semantically the same. They capture the same information for us. And now here, we're in this for loop, we're not looping over each, over just the neighbors, we're looping over everything. And that's fairly inefficient because we have this instant if statement right here that instantly prunes off all of the things that are not neighbors. So this for loop does a lot of unnecessary work, and just by swapping the basically the order of this for and this if statement, getting a smaller for loop down here, things will go significantly faster. And so that's the overall summary of the differences between these two pseudocodes. If, yeah, at this point, I wouldn't expect that like those differences make 100% sense to you, that it'll take actually working with the code and starting to implement it before all those different subtleties fully click in. But you'll want to have those three differences in mind as you're working on this in order to make the implementation go smoothly. Are there any questions about any of these pseudocode?
I have a question.
Sure.
So the pseudocode on the left is just so that we realize how similar it was to the dictionary assignment, but we won't actually be implementing that version. We're going to focus on the right side.
That's correct, yeah.
Okay, thank you.
Great question. Any other questions? Okay, so let's come back over here to the code for a bit. And I'm going to, let's go ahead and Control C this so we can see a little bit more code at once. here, yeah, so that was the shortest path is going to use that pseudocode that we saw before. And so yeah, here's our source and our target being taken in as integers representing the territory IDs. The next function that we'll talk about is this can fortify function. So in order to talk about that, let's talk about what it means to do a fortification move inside of Risk. And actually, I'm going to need that board back to talk about this. So let's get it back. The can fortify function is going to be also using breadth first search, but in a slightly different way. So the shortest path does not consider either the numbers or the colors of any territory, but the can fortify is going to consider the colors. What a fortification move is in Risk is when you have, it's something that you do at the very end of your turn, and when you have a bunch of territory or a bunch of armies on an isolated territory, a territory that can't make any attacks, you can move it to a different territory as long as there is a path from that territory to wherever you're trying to move that stays within your own color. So in this case, I have this 500 units right here on Western Europe, and I might want to move those, say, onto Peru over here to trap in the red armies down here so they can't escape without fighting me. And there's a path that only goes through blue armies in order to be able to do that. And so that's a perfectly valid fortification move. I can move from Western Europe here down to Peru. Let's see an example now of something that's not a valid fortification move. And in order to do that, I'm going to plot a different board. Let's see, here we go. We were previously plotting board 1. Let's plot now board 3. And board 3 is going to have a few more red armies inside of it, and none of these red armies are going to be connected to each other, and so we won't be able to make a fortification move. So like these 500 armies in Argentina, it might make sense for me to move. I wish I could move them to Western Europe or to Ural, but because there's no connected path of red territories in order to do that, there's only blue territories in the way, then I won't be able to make that move. In order to actually implement this, what that's going to look like is over here in the pseudocode. The pseudocode is basically entirely the same thing. The only thing that's going to be different is this for loop line right here. The idea is that what we consider to be a neighbor is going to be different in this new problem, in this fortification problem. And the reason for that is some things are neighbors in the fortification sense if they are both adjacent, so that adjacency list contains the matching territory and they have the same color. So you'll just have to adjust your for loop right here so that it makes that extra check. And that's what this is explaining down here, is that in order to implement can fortify, all you have to do is modify this one line right here. Are there any questions about what the fortification moves can look like? Okay, so the last really important function that you'll have to implement is, let's put that in here, this cheapest attack path. And this is sort of like the main AI related function that it's going to decide if we know our objective is to get to North Africa and we are in Argentina, we're the red player, how can we effectively do that? Which path should we take? That's what the cheapest attack path is going to do, and that's going to implement Dijkstra's algorithm. I think in order to fully walk through the pseudocode, we're not going to have enough time to do that today, so we'll save that for Monday. But I want to show right now what the one more sort of debugging feature that's going to be really useful for all of these functions that you're implementing. And that's how you can actually plot paths on these graphs over here. So in order to check that your cheapest attack path or your can fortify function or your shortest path functions are working, if you just print out the numbers, they're not going to be like super meaningful. It'll help, really help to actually plot them on the board. And then we'll see how to do that. So in order to do that, I'm going to get checkout solution. So now I will have access to, inside of my examples.py code over here, I'll have access to fully implemented versions of these functions. Let's try out the, there we go, the shortest path. And we'll do it here. We'll say path equals board3 dot shortest path. And we want to go from Argentina to North Africa. So we'll go over here in my, oops. What happened? Where did it move me? There we go, I'm on line 26 now. At the end, I need, on my shortest path right here, I need the territory ID for Argentina and the territory ID for North Africa. Move over to definitions. Argentina is 3. I use the slash key again to do searching to find Argentina. And G Shift T to go left over here, type a 3 right here, back over to definitions, and now I want North Africa. So to territory 24. Back over here, 3, 24 like this. And I'm storing that in a variable path. Let's go ahead and print out the variable path. We'll see that that's not going to be a super useful thing for us to look at. Comment this out so it runs real quick. Come down here and let's run examples.py. And yeah, so it tells us our path is 3, then 4, then 24. Well, I don't have those numbers memorized, so that's not really meaningful to me. I can't tell just looking at that if that's like actually a good path or not. And so instead, let's plot it over here. And if we say path equals path, so there's a keyword argument into the plotboard function called path. And then over here, this rightmost argument is the this variable that we created here. And now let's rerun that. And there we go. And you can see it actually draws this black line starting from Argentina to Brazil to North Africa. So this 3 Argentina, 4 must be Brazil, and then, or sorry, 3 Argentina, 4 Brazil, 24 North Africa. Okay, so yeah, that shortest path is fairly, I think, intuitive that that would be the shortest path. Let's do something a little bit more complicated, and let's find the shortest attack path. So using the Dijkstra's algorithm method. So up here, shortest path, change that to shortest attack path from 3 to 24, and rerun that. Whoop. And what's it called? Cheapest attack path is what I called it. So I'm using my backwards search here to go back to shortest. In order to delete everything, I want to delete this word shortest without manually typing backspace and delete. That's annoying. So what I'm going to do is I'll type df underscore. Recall that d is a verb in Vim terminology. And so anytime you have a movement command after a verb, it does that verb to wherever the cursor would have moved before. So I press U to undo. I want to delete from the S, basically delete all of this right here. I know that if I press F underscore, it'll take me to that location. And so if I do DF underscore, it'll delete all the way up to that location. Actually, I really want to leave that underscore alone though. I don't want to delete it. If you type T instead of D, it moves your cursor to the location before the character that you searched for. So if I type T underscore, it moves me to the location before the underscore here. So I do DT underscore to delete up until that underscore in order to not have to retype the underscore as well. And let's change that to cheapest, like so. Rerun this. Here we can see there's a very long path printed out here. Definitely not something that I'm I'm going to be able to tell just looking at those numbers whether that's a reasonable solution or not. And now coming up here, we can see that, okay, their suggestion is going from 500 Argentina through here, North America, down through Europe, and over into North Africa that way. That looks like a pretty good solution to me. I want to really quickly compare this solution, though, to, say, the solution for board 1. So I'm going to go ahead and delete those. Press X after highlighting it to delete it all. 15 GG to come up here, paste all that. F3 R1 to replace, down, down. Capital F3 R1 to replace all of those things. And now it's going to do the same cheapest attack path on from Argentina to North Africa, but on a different board, which is going to have a different cheapest path on it. And we'll make sure that our code works in both scenarios. Now, because these territories right here, Western Europe, Eastern Europe, you all have 500s in them, that's no longer a cheap path to go through Europe. And so it makes more sense to go around, hop in from Alaska over to Kamchatka and down that way. And so as you're working on all of these functions, it'll really help to plot them on all of these different boards using these sorts of examples and getting a good sense of things that way. If you take another look at the test cases down here, there'll be a lot of good paths for you to take a look at. So here you want to know, is this a valid path or not? Well, we can't just know that by looking at these numbers. And so it'll help you if you actually plot them. Similarly, why is this not a valid path? Well, we can't know that just looking at these numbers. You have to plot it in order to know that. See what territories it skips over. And then for all of these shortest paths, the way the checks are working is the same way that the checks on the word ladder assignment worked, is that I don't have the actual path listed anywhere. I just have the length of the path listed. And so if you have an incorrect implementation, your number that you're going to get is going to be too large because these are the actual smallest numbers. Yeah, I think that's a good stopping point for us for today. At this point, you're able to complete the majority of the assignment. The only thing that we have left to talk about is the actual pseudocode for Dijkstra's algorithm and how that's going to apply here. We'll talk about that on Monday. And that's going to be the last thing that we'll have to talk about in this class, that we are really close to the end. So Monday, we will spend talking a little bit about Dijkstra's algorithm, but that's not going to take the whole time. We'll then start the review for the final, which will take up Monday and Wednesday next week. And yeah, and then it'll be final after that. So I recommend before next week trying to do that final practice exam, come up with any questions that you have that you'd like us to talk about next week. My intention for next week is that it's really going to be mostly driven by what sort of questions you all have and things that you'll want to review. Yeah, we'll have the lab again tomorrow on Thursday. You can ask questions and work on either the PyPy project or the or this graph project. And then yeah. So I'll see you either Thursday or next week. And if anybody still has questions about anything today, I have office hours right now to answer those. So I will.
Thanks, Mike.
See you then.